I could hardly think of a more adventurous, dangerous way to explore our area than to scuba dive over 100 feet down into previously unmapped caves. The Wakulla Springs cave system is the largest of its kind in North America and one of the largest in the world. The Woodville Karst Plain Project has mapped over 20 miles of this system to better understand the Floridan aquifer, the source of springs and spring-fed rivers in Florida, and of our drinking water. The project and the aquifer are our topics today. This is Coast to Canopy, an ecology podcast from WFSU Public Media. I'm Rob Diaz de Villegas. Our guest today is Christopher Werner, Project Director for the Woodville Karst Plain Project. Welcome, Chris.
Welcome, Rob. Nice to be here.
Thanks. Glad you were able to make it. Stormy today on the day we're recording. So let's start with the Woodville Karst Plain itself. I think a lot of our listeners probably live on it and don't know that they live on the Woodville Karst Plain. So what is the Woodville Karst Plain?
Yeah, the Woodville Karst Plain is essentially a exposed limestone plain near the coast where the Hawthorne Group sediments and rocks have been stripped away by higher sea level stands in the past.
Gotcha. And so this is a limestone formation, and then...
Yeah, essentially it's the St. Mark's limestone and the Suwannee limestone outcrop in this area, both in Leon County, Wakulla County, and Jefferson County. And they kind of thin to the east, if you will. And the Hawthorne's been eroded away. And most people will notice that when they drive south out of Tallahassee and they go down this really big hill called the Cody Escarpment. And that essentially is where the Hawthorne kind of disappears. And then you're essentially driving on unconsolidated sands and clays from, basically beach or dune type structures that are remnant of those past sea level stands.
Gotcha. And it's also a system full of caves and springs and swallets. And I mean, anyone who lives in Wakulla probably lives close to some sort of swim hole or sinkhole. So talk about sort of the cave systems within that.
Sure. The term karst basically is a geologic term that we use that describes when limestone's exposed to the surface or it has, very thin sediments above it. And usually rainwater is slightly acidic. So what happens is when it rains, right, that permeates through those sands and clays. They're still kind of charged a little bit with carbon dioxide, and they slowly dissolve out the limestone. And what happens is you form all these voids within there. You still get flow of the water and whatnot, but in this area, which is somewhat unique, is you've got 5 huge first magnitude springs. You've got underground rivers for the most part that feed those. And then you've got swallets where you've got surface streams on the surface, particularly in the Hawthorne Formation, up around Tallahassee and to the west and the east a little bit. And as soon as they get to the Woodville Karst Plain, they usually sink into the ground. And those form parts of those underground conduits and whatnot. And so most of the flow is not via surface streams. Most of the flow is captured underground. And so your drainage basin is essentially subterranean at that point.
Right. And so you have water flowing in caves, but it's also kind of stored in the rock itself, right? It's a porous rock.
That's right. The limestones are very, very porous, and they're very permeable as well. And that's basically our drinking water. So it is our aquifer. It's the upper Floridan aquifer, to be exact. In this area, and it provides most of the drinking resources for Leon County, City of Tallahassee, Jefferson County, Gadsden County, Wakulla County, you name it. Everybody's getting their water from the upper Floridan aquifer, and that's the potable part of the aquifer. The aquifer is actually much, much deeper. Unfortunately, you can't drink it because it's non-potable, right? So that deeper part of the aquifer has really high total dissolved solids, and it's probably more influenced by sea level and whatnot. So you get these kind of brackish and salt water, high chloride, high sodium, high dissolved solid type of waters, right? And so they call it non-potable because you can't really drink it.
Gotcha. So let's kind of bring people with you on a dive. So first part is, how do you prepare to go to a place that no one has ever seen before, likely?
Yeah, well, it takes a lot of preparation. We spend a lot of time up front planning some of the dives that we do. We're really standing on the shoulders of giants, people that pioneered this once scuba kind of came into the fold as a technology. That in the 50s and 60s, people were kind of diving into the springs and some of the lakes in the area, and they found these tremendous caves, right? And they'd open up into caverns, and then they'd go further, and they're like, hey, there's a cave here. But they were woefully unprepared, Rob. And there was a heck of a lot of fatalities and whatnot. And so over time, they adopted different equipment with redundancies built in, and they also adapted their techniques. So normally scuba divers, when you see pictures of them, they're somewhat upright in the water. They've got a single tank on their back, and they've got their flutter kick going and whatnot. If you do that in an underwater cave, due to the silt on the bottom, you're most likely going to get yourself into trouble real quick. So we don't advise that for anybody. There's training programs out there that give you that, but it's also the experience, right? So you've got to build experience to be able to do that stuff. And within the Woodville Karst Plain itself, it's fairly unique. We've got shallow, extensive caves. We, run 60 feet deep, 100 feet deep. Other portions of the cave systems are 200, 210, and then places like Wakulla Cave itself have extensive sections that are 285 to 310 feet deep. And so, those are much, much more challenging because when you dive deeper, two of the problems you have is one is that nitrogen in normal air that we breathe, 21% oxygen, 79% nitrogen. That nitrogen becomes narcotic. So the deeper you go, the more narcotic it becomes. So you can't really think. So if you're impaired, right? They used to call it Martini's Law when I was taking scuba diving in the 80s. And basically every 33 feet, it's like having another martini, right? So you think about that and you're like, well, would I drive my car on 4 martinis? Probably not, right? Not a smart thing to do. Well, it's the same thing in cave diving. So we've got that problem. The second problem you've got is the deeper you go, the oxygen becomes toxic to your body. And so, humans have grown up on the surface of the planet breathing air, but that 21% oxygen, if you take that to 300 feet, you're most likely going to have a convulsion because it's toxic to your body at that partial pressure. So what we do is we cut our mixes with helium for those deeper depths, and we've kept increasing that helium over time. And so when you dive deeper, you get past what's called the recreational no decompression limits, and then you've got to decompress before you can come to the surface. It's kind of the opposite of mountain climbers. You would hear mountain climbers, they can't just race up from, wherever they start at base camp or the hiking trail or whatnot. They've got to acclimatize. That acclimatization is essentially decompression, right? But we do it in the opposite order than mountaineers do it. And so we start our dive, we can go down, we can, start going, go explore, go to places that nobody's ever been before. We put in a continuous guideline the whole way. We take surveys of that. We make notes of water flow, creatures that we see, potentially artifacts, potentially, interesting geologic formations and whatnot down there. And then when we come back, we've got huge decompression obligations before we can surface. And so in some places, those aren't too bad. It's a few hours. In other places, depending on how long you stay at those deeper depths, you could be talking 8, 10, 12, 16, 20 plus hours of decompression. And so if you're going to do something where your bottom time is 2, 3, 4, up to 6 hours, and you're talking about decompressions that can be anywhere from 10, 12, 14 hours, all of a sudden you're having to plan for a 24-hour dive.
Right.
And so there's a lot of things that we do and we've implemented over time to try and make that, take out a lot of the risk, manage it in a way that we can get everybody in and out safely. And so that's probably what we're known for is our standards and our procedures, because they've been built up over a number of decades and they keep us safe and they allow us to repeat those dives over and over and over again safely.
Wow. So before you go into a cave you've never been in before, how much do you know about it from whatever you can sense from the surface? I mean, how do you know what to expect?
Yeah.
Or how much can you expect?
It's a good question. We kind of know that, well, it's water filled. We don't know if it's going to go or not. So you pull up to a sinkhole or, a landowner contacts us and say, hey, I've got this really interesting sinkhole. It's been here for as long as I can remember when I was a kid, when my father owned the land or whatnot. And we'll go and we'll talk to them about it. We'll look at it. We'll ask them things like, has it changed over time? Has it been sinking? Have you put anything in it? Have you tried to, drop a rock tied to a string and figure out how deep it is? Right. Those kind of things. But usually we don't know very much. Usually if they're clear, and the rest of the cave systems are clear, okay, maybe it's spring fed or it's got some kind of connection to an active flowing. If it's dark, that usually is a better sign that it's going cave. A lot of the Apalachicola National Forest is drained into some of these swallets, and that is really, really tannic water. So that dark brown that you see, that kind of red tannin color, the tea color of the water there, that would tell us that, hey, this probably is connected to something. A lot of times at the bottom of the sinkholes, there's, tree limbs or even tree trunks in some cases, lots and lots of silt, a lot of leaves and stuff. And so you get down there and you kind of see, okay, is there opening? Do I see a head wall with some exposed limestone? That's always a really good sign. And then, usually there's a restriction. I got to move some of those tree branches or some of those leaves and some of that silt out, and you run a guideline straight from the surface. And then once you can kind of get in, sometimes they go, sometimes they don't go. So we've been in a couple over this past year that don't go anywhere. They're beautiful, but they go, down to 50 feet or down to 80 feet, and then there's a small cavern and there's not much else. But then sometimes you get really lucky and you've got good flow, and it's usually what we call offset sinks. So you'll come into a passage that's offset, and it's got an upstream section and it's got a downstream section. And when we get that, we know that, hey, there's a lot of cave to explore here. And so what we're usually doing is we're using a combination of old USGS topo maps. We're using a combination of LiDAR to kind of tell, okay, where could this be connected? We're plotting up where other sinks or caves are in the area. How close are we to this? How close are we to that? What was at the end of the line in that other cave? Was that close here or whatnot? And so we're always trying to use that information to figure out, hey, could this be connected to something?
Gotcha. So when you explore like you said something about going 5 miles in, that's not one of those where you go in not knowing ahead of time. So is it a process of sort of going a little further? And
that's right. Yeah. Nobody on their first dive is going 5 miles in a single shot. That's a very rare occurrence, and the logistics of an operation like that are, you're talking about a week to 2 weeks of preparation, and then you're talking about 3 days to kind of execute that, right? Because you'd have setup teams, cleanup teams. You got a lot of support. You got a lot of support divers in the basin to follow. Usually, what we're talking about in new exploration is you put some line in, you come back, you plot that up. Okay, where's it going? Did you guys feel flow? I felt some flow. Hey, I saw a catfish. That's a good sign. Did I see any other life in there? Those kind of things. Flow is basically the biggest thing that we would focus on. And so, it's a progression, right? So the first time you go, may not find much. The second time, okay, I know it's about this deep. It seems to be that deep, but just in case, I'm going to take a little bit of deeper bottom gas, and I'm gonna look and I'm gonna see, where we can go. And so it's a progressive thing. So you'd tie into the old line and you'd explore onward, and then you'd survey that and you'd bring that out and see where that goes. Okay, next weekend we go and we do it again. So it's a very progressive type thing.
Gotcha. So what do you see? So, I mean, you see when you get down to a certain depth, I mean, you're only seeing what a light shows you. So talk about that aspect of it and sort of as you find your way through, I guess, whatever the beam can show you and whatever the clarity of the water is.
Yeah. I mean, those are the two biggest things, right? The clarity of the water is enormous, right? So when people always ask, well, what do you see down there, right? But a lot of time it's more about what you don't see, right? And so the caves in the Woodville Karst Plain, and especially in Wakulla Cave, I mean, they can be really small passages where, basically just a human with maybe a couple tanks on can fit and not much more. But they can also be these enormous passages that we refer to as Tallahassee Power Cave. And when you've got Tallahassee Power Cave, you're talking widths anywhere from 60 to 100 feet wide, and you're talking 40 to 60, sometimes 70 feet high. So, you can fly a jumbo jet through these things. They're that big. And when the water is clear, your light can't see the walls, right? It's that big. So you're kind of, diving into an abyss. It's a different world altogether. It's almost a surreal experience in some. And so, you're talking with a guy that's been on the Woodville Karst Plain Project for 30 years, right? So I've kind of gotten accustomed to that. But when you can break into some really new cave and it's big and it's going and whatnot, and you just see a lot of different rock formations, the way the water has carved out the limestone itself is just, some of these things are really beautiful. Sometimes you can see that contact between the St. Mark's limestone and the Suwannee limestone. Sometimes you also see remnants of when sea level was much, much lower, where you'll get a cross section of a passage that we call a keyhole passage. So, it's kind of spherical on top or an oval on top, and then it's got like a small canyon cut out in the bottom of it, right? That tells you that when sea level was lower, the water table was also lower, right? So that water table of the aquifer was much lower. And in that cave passage, at one time, when sea level was low like that, that was a stream cutting out and dissolving away that limestone. It had free surface, just like the streams you'll see in areas of Tallahassee or in areas of the Appalachian Coal National Forest. Those type of things are really, really indicative. Now, you need a trained geologic eye that has a specialization in right. Karst geology and hydrology to notice those things. But at the same time, it's remarkable. The other thing we see down there is a lot of life. Like people wouldn't imagine, how much life is down there. So we always see catfish. They seem to go everywhere. We don't know how far they'll go from the light and whatnot. I've not seen any albino catfish ever. However, there have been other places in Mexico and some other caves in Europe where they found albino fish, which means they haven't been exposed to light in a really long time. And so they lose all the pigment in their skin and whatnot, right?
Yeah.
But we find all the time albino crayfish. There's all kinds of amphipods and isopods. These are really small things that kind of float in the water column. And so, all these places that you've got sinkholes or these karst windows or swallets that are taking some of these stream waters in, you're getting everything that's kind of in the forest or on the above ground going into that cave passage, right? And so a lot of that stuff has nutrients. It's got leaves and other things that these critters can eat, and that's how they survive. So a lot of places we see stuff like that. And then there's a lot of silt, right? And so that silt gets built up in different ways, and you get dunes. And so, if you're in a really big passage and then that passage kind of closed down, you'll see that you start to get ripples on the floor. If the passage opens back up, then anything that was carried along with the flow, that kind of drops out of suspension, and you'll see these like dune-type structures in places. And then there's places in the cave where the ceiling, the cave gets so large that the ceiling, kind of breaks apart. We call it breakdown. Cavers call it breakdown. Well, it's in the cave too. So you get these big, large rocks, and then they're usually covered with silt as well. So it's a really, really unique environment. I find it really, serene and calm. I know most people would not feel that, but at the same time, it's the darkest place on Earth. Yeah. It never sees any light. Light can't penetrate through rock. So, the only thing you carry with you is your primary light and 2 backup lights usually. Sometimes you'll carry a video light or a spare light beyond that. But, our lights can penetrate pretty good if the water clarity is good. If the visibility is good, you can see a lot. But a lot of times when the cave is big, you can't see the ceiling, you can't see the walls, you can't see the floor. So if you're exploring that, you're kind of either staying on the floor or you're staying on one wall. If you can't see that other wall, and you're in pretty big cave. And so that's the exciting part of it, right? That's the thrill, is the exploration and realizing that you've got skills and a unique opportunity to kind of see something that maybe nobody's ever seen before or nobody's described before. So in the past few years, we've been taking video cameras with us. In fact, we've been taking cinema cameras with us, record in raw recording, right? So, and in that way, we need tons and tons of light. Much more light than you would think, right? Because this is the darkest place on Earth, essentially, and you need to light it up. And when you can light up some of those big passages, you can see the enormity of how big these caverns are, right? And I think, every time that kind of gets to you, like, wow, this is really a big space. But it's only 100 or 200 feet below the ground surface, right? And so that's really hard for people to wrap their heads around, is how extensive some of these cave systems are, right? Like Wakulla Springs, right? That cave that emanates at Wakulla Spring, we've now mapped and surveyed nearly 45 miles of underwater cave just from that one spring. Wow. Now, it took decades upon decades to connect all those things. And, we had these separated little caves, and one by one, we've just been connecting them all together. So it's a really big system. And for somebody like me that's a scientist, right, and is trained in geology and hydrology, for me, it's like that's part of the mystery as well. It's like, how does the hydrology of that area work? What are the things we're missing? Because we don't have a complete picture. And I think that's the odd thing that people, probably still don't realize, is how little we know about how these things formed, how far that cave system goes, how extensive it is. And a lot of the times we are beholden to, visibility, right? So when it rains a lot, that usually means that all this stuff gets washed into the caves and visibility goes way down. Other times, right, when we get droughts, we really like droughts. I know people don't like that for their lawns or whatnot. It's dusty or, the forest catches on fire and whatnot. But for us, that's the best time because we're not getting a lot of those surface inputs into the system and visibility is usually fantastic. And so those are the times where we're most active, but we're highly dependent on the weather.
Gotcha. So you talked a little bit about your training and having that geologist's eye. So what's your background and how did you get into this specifically?
Yeah, so I did a bachelor's degree in Earth and Planetary Science at the University of Pittsburgh with a minor in math and physics. And I just like geology. I just like the natural world, right? So that was really why I liked physics and stuff. And if you're going to do that, you got to know math, right? And then I came here for my master's degree here at Florida State University, and had a fantastic committee and a major professor and whatnot. And I really came here to dive, right? Because I wanted to get involved with the team. I thought what they were doing was really great. But I also had that curiosity of, what does this system look like, right? What does the cave system do? How does it all connect? How does the regional geology affect what's going on in that upper aquifer? And I've been studying that for a long time. And so then, I ended up doing a master's degree in geology, and then I came back to FSU one more time after a short stint of professional career. I came back for a PhD, and I got a PhD in geophysical fluid dynamics. So, more about the water, how it moves, how it can affect things and whatnot. And so, it's always been a curiosity to me, and it's just kept drawing me in and in and in as we go. And I was lucky enough during that PhD program to the Springs Initiative funding was going on at the time in the early 2000s, and there was projects. So there was money, there was ways to study that and incorporate a lot of things that we were doing on the diving side with the science. And a lot of the Springs initiatives in and around the area of the Woodville Karst Plain. We did a lot of dye traces at the time. We did a lot of other studies that were really informative. A lot on the ecology of Wakulla Springs. At the time, they had that explosion of hydrilla, and the nitrates were somewhat elevated at levels and whatnot. We were trying to figure out where all that's coming from and whatnot. But it was also, all these sinking streams that we saw that you can't really get into because there's no way to kind of safely do that. But with dye, it's just going to go with the water. And so we were tracing a lot of the sinking streams or swallets in the area. And so, putting together how the aquifer functions dynamically was really probably, one of the most fulfilling things I had done in a while. And so, worked on that for quite a few years and whatnot with some colleagues at Florida Geologic Survey, colleagues at Florida State University, a whole bunch of great consultants. Consultants are essential because they bring expertise in places that you may not have that expertise. And so with those guys and whatnot, we got a really good view that a lot of the things that we were seeing affecting not only the food web and the ecosystem, and with it the wildlife counts that were kind of changing and whatnot, that was all being fed by the water. So if you understand the way that the water flows to some of these large springs like Wakulla Springs, then you can understand what's going on with the ecology and the food web and whatnot, and how that's adapting to changes, right? And a lot of those changes, a lot of them are natural, but some of them are also, human induced at times, right? And so it's like a puzzle that you're trying to peel back the layers of the onion to get a fuller and fuller look, but yet you never have enough to kind of completely figure it out, right?
Right. And so let's talk a little bit about the mission of the Woodville Karst Plains Project. I mean, there's a lot of questions we have about, why is the water darker than it used to be in Wakulla Springs, or where can a gas station safely be put, in Wakulla County to not affect, or there's a lot of questions we have about connectivity and all of that. So talk about, it's fun to explore it, I'm guessing, and it's cool for us to know it. I mean, for the public, it's like, wow, that is amazing. But practically speaking, what are the kinds of questions you hope to answer?
Yeah, well, I mean, one of the things we've done over the past years, we've changed our mission, right? Our mission used to be to simply explore, survey, map, and document things, but now we've really turned more towards the exploration. But now we've added the science, right? So if you want to know about something, the best people to talk to are the people that visit that on a regular basis, visit that type of environment. And we find out that, due to changes in faculty at a lot of the universities, due to changes in state government, even federal government, who, kind of have done studies in the past and whatnot, that legacy of knowledge doesn't get passed on and it gets broken up. And then you've got an organization like the Woodville Karst Plain Project, which essentially knows a huge amount of what's been done because we've been part of helping them put instruments in the cave. We've been helpful in doing some of the dye traces and where we're going to inject and where we're going to monitor and things like that. And so, that knowledge built over time, I mean, we haven't lost any of that. We're probably the ones that have retained it the most. And so, we've been working with some new researchers in various aspects. We've still been working with, our friends in state government. They've been very, very supportive of us, as well as the federal government. And what you find is that we probably know a lot more about how things are working than they do. And so when you've got, folks like myself and some others that are more technically oriented or scientific or engineering oriented, we can do the things we do as far as the exploration, but then we can bring that scientific knowledge. So we really are useful for them to help close the gap and then to ask better questions, right? And so a lot of times it comes down to local county administrators or local county board of commissioners that needs to make decisions. And they sometimes they don't have the expertise. And then, they'll bring in a firm or whatnot. But that firm, a lot of times that, they use as consultants and whatnot, or somebody puts a development proposal together, they may not understand some of the uniqueness of the area. And so, folks like us can provide that, right? There's a lot of really good consultants out there. But at the same time, the depth of knowledge we bring about the area is somewhat unique. And I think that's been recognized by Florida Department of Environmental Protection. It's been recognized by the Florida Geologic Survey. It's been recognized by the Florida Park Service. And so, a lot of times we've got knowledge that nobody else has. And so one of the things we're turning to more now is to help aid in directing some of that science forward, but also to benefit, local citizens and counties and whatnot to make better decisions or be fully informed before making decisions on different types of development or development planning issues that I think everybody should be concerned about. And so, folks like, City of Tallahassee, other folks, I mean, we regularly will have conversations, we'll attend meetings that they're at. I mean, we work with the water management districts a lot. So, in a way, we're kind of this nonprofit organization that is there to serve everyone, right? And we don't pick sides, we don't play politics. We're very even keel. We think that if our knowledge can benefit someone and we've got the resources to do it, then we're going to try and help. And a lot of people that we help are landowners, right? They're saying, hey, I've got this sinkhole, or I was thinking about putting my barn here. Is that a potential problem, or where should I locate it? This is my land, and whatnot. And so we get lots of calls like that. to try and help folks, right? And so that's what we're in the business of, is trying to help folks. And one of the ways we can do that is bring our scientific expertise, our experience, and the exploration capabilities that we've got through decades of service to the community to help bear on challenges that both citizens, county, city administrators, as well as Joe Q public is concerned about.
Right. And there's a specific instance you mentioned when we had our pre-interview about the location of a gas station, and so talk about that as far as I guess helping people figure out where's a good place to put something like that.
Yeah. And so, this happened in Wakulla County. A refueling station was proposed by a company. But little did they know it was over a cave that had been well mapped and well established for over 40 years. And so we knew where that passage was. There was no doubt about it. We went in to gain additional information. And at the time, we were working to try and connect that cave into the Wakulla Cave system. So that name of that cave was Chip's Hole. It had been explored for 40 plus years, Rob. It's not like it was new. And it was sitting on a piece of St. Joe Paper Company property, and it had been there for a really, really long time. But nobody seemed really motivated about it. And, either the company didn't do their due diligence or it was just kind of missed by their consultants or the firm that they hired to, kind of do an environmental assessment of the property. And that's a place where, we don't want that to happen again, right? So, getting tools that county administrators can use, like city administrators can use, and it's there and it's available, we think is really, really important. And so in that case, finally, we were exploring there. We had an ongoing, nearly 10-year effort to try and connect that Chip's Hole Cave into Wakulla Cave. And in January of 2023, we were successful. But we had been trying for a really long time at that point. And so what we used is we basically turned to the science. We did our own dye trace at the limit of exploration and monitored, I think it was 16 different sites along the main Wakulla Cave passage to figure out where that dye was coming into the system. And, of those 16, 14 came up with no dye. Right. But there was 2 that did. And so we knew it had to be, just upstream of that first one that got the dye hit. And lo and behold, we found the passage. The guys went in. They executed, I don't know how many dives. It was quite a few, probably upwards of 15 or 16 different dives. But it was really small passage. It was something that we had, kind of. It's not the first place you'd want to go explore. Right. Let me put it that way, right? So it's low, it's silty. There's flow, but at the same time, it took a lot of perseverance of those guys to kind of finally make that connection. And when we did, we had the science that was telling us from the dye trace, well, we know this is connected. And then when we made the physical connection, I think that was a rallying point for a lot of the environmental groups that were opposed to that refueling station, because it kind of gave them some ammunition to see, look, this is connected directly to Wakulla Cave and Wakulla Springs. And so in that way, probably siting a refueling station over a cave that's 80 to 100 feet deep is probably not the smartest thing to do. And so, that being said, we're not against refueling stations. We're not against development in Wakulla County. But at the same time, there should be an honest discussion about, okay, where are we going to put some facilities versus what areas should be, we should be a little bit more cognizant of on can affect places like Wakulla Springs. And so that's the kind of dialogue that I think most people want to see. And I think, making the most informed decisions that you can are probably the right way to go.
Gotcha. So you've mentioned dye traces a few times. So for people who don't know what dye traces are, talk about sort of how you execute that and sort of how helpful that can be for passages, like you said, that maybe people cannot, or sometimes where there's not a real passage.
Yeah.
As far as connecting two
and
locations.
A lot of times, some of these passages may be too small for a human to fit through. And so, in a lot of cases, what you do is you take a fluorescent dye that has got a certain wavelength that, if you shine light, a certain wavelength of light at it, it will fluoresce. Okay, and so that's the first thing. And the second thing is then you've got to monitor a whole bunch of different places. So a lot of different springs, a lot of different sinks, other places, like, some of these karst windows that I may eventually get to. And so, we had been doing that on a regular basis during the Springs Initiative work in the 2000s, in conjunction with Florida Geologic Survey and Florida State University, and we were really successful in a lot of those dye traces. But they also highlighted how complex that underground network of passages was, and that how, depending on the different hydrologic conditions that were present in the aquifer, sometimes dye would go one place, and then at different times and a different hydraulic regime, dye would go someplace different. And so I think that's the part that makes it really confusing for folks that aren't trained in that type of stuff, because it's beyond what you learn in your undergrad or even a traditional master's, right? You have to get a lot more specialized, especially into karst hydrogeology, and that's a very useful tool, because in some cases you can do qualitative and just say, okay, I'm putting in dye here. Where did it come out, right? And so you can check where it came out. And in other cases, the much more effective way to do that is quantitative dye tracing, where you put a known amount in, and then you've got samplers that sample every so often, say it's like every hour or every few hours, and you get that, and you take that back and you look at it under a spectrofluorometer, right? Or you can use some of these newfangled gauges they've got that does that. But one of the problems with those, or the challenges with those, is the turbidity of the water sometimes, right? That can really affect, and it can shift that wavelength. So a lot of times people don't do that step. And then, we got to kind of look at their results and say, maybe not as rigorous as it should be, right? But doing those quantitative dye traces gives you travel times to the peak. It gives you things like dispersion within those conduits, dispersion of longitudinal and latitudinal dispersion, and give you things like, Peckley numbers and Reynolds numbers and things like that for a fluid dynamics guy are quite important, but they go to how you would model that going forward. And so, there's big emphasis in science over the past 20 years, maybe even 30 plus, of trying to model things that we understand the basic physics of. And that can be really, really useful, but it can also be really, really problematic, right? So if you don't have enough variables to define what's going into your model, it's kind of the old garbage in, garbage out, right? And so, the way we try and talk about it is that, okay, let's get really, really specific about what we need to capture from some of those quantitative dye traces. Let's then implement the conduit system first, because that's where the majority of your flow is. It's not in the pore spaces of the rock. That's probably much, much lower. There's probably still flow there, but compared to what's flowing in the conduit, not even a comparison. You're probably talking 2, 3, 4, orders of magnitude difference, right? So most of your flow is within the conduit systems in karst settings, and a lot of people don't understand that, right? So that's why it's really important to make good decisions about where these underwater caves are. I mean, you can't change where the cave is. Nature put it there, right? The only thing we're doing is going in and kind of exploring that, and then we're able to give some of that data to the scientists so that they can use that to model, right? But even then, it's somewhat crude. But the quantitative dye traces with the exploration, all that science combined, and then you do water quality on top of it, you do isotopes and whatnot, using the water as like a fingerprint to figure out what's happening in the system, right? Because it's really easy to look at a surface stream and say, oh, the water flows there and then it flows to the Gulf, right?
Right.
Unfortunately, right, when it's underground and you can't see it, you really don't know where it's going. And so, one of the things I recently gave a presentation to the Wakulla Environmental Institute down in Wakulla County, and I talked about, what we know, how we know it, and more importantly, what we don't know, right? And there's a lot of things we don't know, and it would be fantastic if we had more information to kind of get a better view of what those things look like. But that's got to be done very rigorously, right? Like the science has to be, we've got to have very good questions we're trying to answer, and we've got to have a hypothesis to test. And I think a lot of times, we see folks that are just trying to do some science, but they're not really testing a hypothesis. And so, I would steer people away from that because, science is about testing hypotheses, right? And if you get a result that's different than our hypotheses, then it basically tells you your hypothesis is wrong and you better come up with something different. And that's the way you kind of progress science. And so a lot of times I will hear the phrase, follow the science. Well, if you're going to do that, you're probably going to have whiplash because science is messy. Sometimes you're going to get a picture that tells you one thing, you're going to get some results that may point you in a different direction and whatnot. The science here is not settled by any means. And so I think there's a lot of fields where the science is not yet settled, but if we can help solve some of those things, I'm all for that. I think most of our membership and our divers, they want to see that happen as well.
Yeah, yeah. And so as far as like what we know and what we don't know, I guess a lot of us are curious about, and we've heard a lot of different people's hypotheses maybe on the dark water in Wakulla Springs. So yeah. What do we know? What don't we know about that?
Yeah, so we know that by a set of proxy data, right? When I talk about proxy data, it's like, we haven't really measured the clarity of the water. What we've done is the Park Service has tracked how many glass bottom boat days per year they can run the glass bottom boats. So if it's really, really dark, they're not offering glass bottom boat tours because, well, you can't see anything, right? And so what we've seen since around the mid-90s, that has decreased precipitously. And probably over the past 5 or 6 years, it's been basically, 1 or 2 days a year, sometimes no days per year, right? Which is telling me as a karst hydrologist that essentially what we have is we've got an unknown source of water coming into the Wakulla Springs Basin somewhere, and that is likely, most likely, probably going to be some type of surface water or additional swamp that's now draining in. And so I think the concept of drainage basins, what most people think about is surface water drainage basins, right? So if I drop water on top of a mountain out west and it goes to the east, it's going to flow down to the Mississippi eventually. Right. If I put it in the west and that drop of water goes west, it's going to pick up another river and it's going to make its way to the Pacific Ocean somewhere. In karst basins, it doesn't work like that, right? And the reason is because you've got all these cave passages and these conduits going every single different way. And depending on how much rain you've got or different hydraulic regimes that are going on inside the aquifer, right? Sometimes when you put water in one place, it'll go to point A. The time you do it, the second time you do it, it goes to point B, and then you're left with, well, why is that? Well, what we see in karst basins is that the drainage basins overlap to some degree. And so, if there's a lot of heavy rain in Tallahassee and we've got Leon's sink system down to Wakulla Spring is just screaming, well, guess what? If you're adding additional water in a nearby basin, that may not go to Wakulla. It may go someplace else. Say it goes to Spring Creek or it goes to Wakulla Springs or, something like that, over to the St. Mark's River rise, let's call it. But if you haven't had a lot of rain in Tallahassee and it's really low hydraulic conditions, and all of a sudden over parts of the St. Mark's River rise, basin, you get tremendous amounts of rainfall. All of a sudden it can't all come out at the river rise, right? And so that overflows into the Wakulla Basin and would essentially flow to the Wakulla River somewhere or to a set of springs that outflows either Wakulla Spring itself or something like McBride Springs or some of the other springs that we know are along the river. So you get these really complicated kind of feedback loops. And I think the biggest challenge we've got is that we're monitoring quite a few places, but we're not monitoring enough that we can tell exactly what hydraulic conditions would influence something else. And so, as far as the dark water in Wakulla goes, I think my personal view is we're missing a source of water somewhere. Now, I don't have a lot of evidence for that just yet. However, we were working with Florida State University Coastal and Marine Lab on a project, and we're still waiting for some data to come back. But my guess is that's probably going to show that we've got a source of water that we previously didn't account for. And that's probably why we're seeing, higher frequency of dark water days at Wakulla Springs.
Gotcha. And you talked about that starting in the mid-90s. And so a lot of stories I cover have to do with these longer, harsher droughts we started experiencing in the mid-90s. It's affected a lot of different things. And so part of that might be a change in just the recharge of the aquifer or usage, or there's so many different.
Yeah, there's a lot of things that go into that. Usage is one, and we've seen that kind of peak in Leon County. I don't know if we've seen that peak yet in Wakulla County, but the population's a lot less.
Yeah.
And if you look at the long-term averages for precipitation, both in Leon, Wakulla, Jefferson counties, over the course of 10 years, it fluctuates a little bit here and there, a few extra inches for a few years, and then you get into a little bit of those deficits. However, we haven't seen huge changes in that. And that usage, even though the populations are increasing, the usage hasn't gone up. In fact, in Leon County, over the past 5 or 6 years, that usage has come down a little bit. And that's probably due to more efficient faucets and showers and toilets and stuff like that people use. And I think while those things are important, it's not clear that that's changing the total amount of water we've got in the upper Florida aquifer. At least the data that I've looked at hasn't suggested that yet. There probably is something to do with these overlapping karst basins. And so, those change over time. And so, if you were thinking that the Woodville Karst Plain and Wakulla Cave, pretty much resemble what we've seen up in Kentucky around Mammoth Cave, It's been pointed out there because the local universities, the Park Service did a lot of dye tracing. They did a lot of, and that cave is dry, right, for the most part, except for a few underwater passages. But you've got the ability to kind of map that out, and that cave is nearly 400 miles now, or maybe even greater than that. And those dye traces show that depending on stage height of the river there that flows out to, called the Green River, you'd get dye going in different places. That's probably what we've got going on here as well. The problem here is we can't explore all that cave because we don't have the best conditions all the time, right? And the farther south you go, the closer to the coast you get, the conditions the visibility is really a challenge. Now, there's ways to figure that out, right? So I talked about the isotopes, right? You can use various isotopes, and that's just a fractionation between, things, in the atom. You'll get alpha decays or beta decays, and it changes that structure a little bit, and that'll show up. And so you can look at some of those ratios. You can use sulfur, you can use uranium, you can use deuterium. You can use a lot of these different type of isotopes to give you a sense of, is that meteoric water that I'm seeing? Is that deep-seated lower Floridan water that I'm seeing? Is that something else, right? Is it marine water or whatnot? So you can use those to kind of type source locate. Okay, what was the ultimate source of that water kind of coming into the different basins? So we're in the middle of that right now, and I think we'll be able to complete that hopefully by the end of the year, maybe first part of next year. But I think that's going to tell us a lot. And the real challenge that we were trying to solve with that study was more around, are we seeing marine waters from the Gulf make their way up to Wakulla Springs? So we were trying to figure that out. And one of the things, besides the dark water, the other kind of mystery that we had at Wakulla Springs was these high conductance events. So, the conductivity of the water, you were getting these spikes up. So they'd go from a background of around 300 microsieverts per centimeter. I know technical talk, but anyway, that's basically what you'd have emanating out at the Wakulla Spring and Wakulla River over a long period of time. And then you're seeing spikes up to 400, 500, 700 in some cases, upwards of 1,000.
And you're talking about
in a few
sorry.
Yeah.
I just wanted to clarify for conductivity. So we're talking about the ability to conduct electricity in
Yeah,
water?
it's exactly what it is,
Okay,
right? It's
right.
basically it. So the more ions that you've got in the water, the easier it would be to conduct electricity or electric current through that water. And so that's what we're looking to. People call it conductivity, and we can talk about it as conductivity. But you were seeing these spikes, right?
Yeah.
And over the past, let's call it 18 or 19 years, we've seen 14 of those on record, right? We've seen them at the spring, we've seen them in the river, and we're trying to figure out, okay, what is that? Some people had the hypothesis, some FSU researchers in the past, as well as the USGS, that maybe you had water from Spring Creek at the coast that was working its way up the conduit system and getting expelled at Wakulla Spring. I had my doubts about that. We're still trying to figure that out. That's what we're waiting on, some of the final isotope data to tell us. But we should know that relatively soon once we get that back from the laboratories. And I think that's gonna tell us definitively whether that's true or not. So some people have made the jump from the conductivity to this has got to be salt water or seawater from the Gulf. And that's the part where, okay, maybe you've got one variable you're looking at, right? Like that may not be it, right? Because there's places we can go out to, some streams and some swamps and whatnot, where you've got, depending on the exposed rock you've got and whatnot and how long of a residence time that water has in that swamp, I can show you high conductivity waters coming in. And so, that's one of the things I caution people with is we probably don't have a a really good understanding of that yet to say that one way or another. But I think soon, following this study, we will have that. Yeah. So there's two mysteries going on at Wakulla that we're trying to solve, and you know, I think these are worthwhile pursuits, right? They're worthwhile pursuits for, you know, the public. They're worthwhile pursuits for the universities as well as for the Woodville Karst Plain Project, because it's going to take everything we've got combined to work on that problem together, right? Like, you know, solutions just don't present themselves out of nowhere, right? It takes the combined effort and expertise of a lot of different, you know, professionals to bring to bear what needs to be figured out to solve some of those problems.
Gotcha. So you've talked about the need to have more monitoring at a lot more different places to figure out how, you know, the water is moving around. And there's obviously a lot of questions to be answered. So what are sort of your priorities as an organization going forward for the next couple years?
Yeah. So one of the things we've been a part of and we're working out the final details on is this last legislative session. There was money set aside by the legislature in the form of a grant for the next, you know, several years, the first year of funding, obviously getting the green light, to map Wakulla Cave in its entirety in 3 dimensions and to make sure that every place we believe that is, we'll do these detailed underwater surveys of that with a robot. And so we're going to start on that hopefully soon. We'll get those contracts in place and whatnot. They're moving along. But that's a really ambitious project. And so we are partnered with both the state, we're partnered with FSU, we're partnered with University of South Florida. We're partnered with an organization that's got the robot called Sunfish, as well as us, to bring our collective expertise together. And the goal of that project is really to be able to map these caves out in 3 dimensions, get them into a system like an ArcGIS system that allows, you know, county as well as city and state resource managers and administrators to have that data at their fingertips so they know, hey, this is where that cave is. You know what? We probably want to limit any type of development we've got in or near this, right? And then as time goes on, we'll be completing parts of the cave. So I think for the first year, we've got the goal to map 7 miles of that 45 miles of cave, and then we step up to 12 and 13 miles per year after that. So it's an ambitious project. We're excited about it because we believe once the public can see the cave in its entirety in 3 dimensions, they can see the extent of it, and they can, you can figure that once you model this, right, you can display it in different ways in 3 dimensions with fly-throughs and kind of show, different land use planning and things like that. That's going to be a tremendous resource to not only the citizens of Wakulla County, but also of Leon County, because that cave stretches up into southern Leon County. And so I think, once people see that, they're going to be like, wow, this thing is enormous. I mean, I tell people, right, if they could see what I've seen of the cave system, this would be a national park. It's just that it's underground, underwater, and you can't get to it. I mean, this is as spectacular, if not more spectacular, than what I've seen in Mammoth Cave. And I've spent a lot of time at Mammoth Cave, right? So I know how big that is. And the stuff I've seen here is even bigger and more extensive.
So getting into my last couple of questions here, but you mentioned having people see this, and so you talk about getting cameras down there. Talk about that aspect of it. I mean, for I guess seeing is believing, and just sort of how you communicate this to the public and get people to sort of wrap their heads around what's going on, sort of beneath our feet. When we're down in Wakulla and South Leon.
We try and do that. We're really limited, Rob, by the visibility sometimes, right? And it's a whole planning process that has to go in because, like we talked about before, the caves it's the darkest place on Earth, right? Like you might as well just be in outer space, not ever seeing a star, because that's what it's like. And so you got to bring a lot of light with you. And then you got to have guys on scooters with that light so that, when I've got the camera and, we're using cinema cameras now and we're recording in raw format so that we can kind of bring out the, lower the darks, raise the midtones and whatnot, and have people see that. It's somewhat awe-inspiring to people, I think, that how beautiful it can be. And it's probably worth something that's protecting, right? Because, it's a whole process to do that. And so I think what we're planning to do is during parts of this project, we're going to do a lot more filming and kind of get that out. We'll get it out on YouTube. We'll get it out on our webpage. We're revamping our webpage now. We've got Facebook, so people can follow us on Facebook at the Woodville Karst Plain Project. And we're getting a lot of that stuff out, and you'll see a lot more of that coming because we think connecting people directly with what's underneath their feet probably will bring a groundswell of, hey, these are really worthwhile projects that we're working on. And the other piece of it is, if we can successfully do this three-dimensional mapping, by that time that fourth year comes around and we get that all together, I think people are just going to be absolutely dumbfounded by how big this cave is and how extensive it is, and it's right beneath our feet. So I think people are going to get really excited about it once we can show them some of that stuff.
Great. Well, thank you so much, Chris Werner with the Woodville Karst Plains Project. Thank you for being on Coast to Canopy. This has been a really fascinating discussion, and I'm really looking forward to seeing a lot of what you find in the next few years.
My pleasure, Rob.
During the podcast, Chris Werner talked about peeling back the layers of the onion to get a fuller look at the aquifer. He was talking about doing this through research, exploration, and measurements. WFSU Ecology has done the same thing, but through videos, blog posts, and podcasts. We've explored the Oscilla sinks and the Lake Miccosukee sinkholes with Florida's state geologist. We've documented the Porter Sink drydown in Lake Jackson and how wildlife responded to fluctuating lake levels. Chris talked about creatures that evolved to live in cave systems and about the Wakulla Springs wildlife surveys. We've done stories on both. You can find links to all of those stories on the illustrated version of this podcast at wfsu.org/ecologyblog. All of this work is made possible by viewers and listeners like you. If you want to support this podcast and the other ecology work we do at WFSU Public Media, you can join the WFSU Seed Circle. You can join for a $10 a month donation, and we'll give you a shout out on this podcast for a year if you want. Thank you to David Blair, Carol Goodyear, Chris McFarland, Carrie Maddox, Clara Mullins, Alina Pryor, Kim Sash, and Donna Tharp. This has been Coast to Canopy, an ecology podcast from WFSU Public Media. Today we had Evan Rossi running audio and Ian McGordy running the cameras and digital video post-production. The music at the start and the end of the show was by Tallahassee's own Tracy Hornbeam. Photos and videos of cave dives were courtesy of the Woodville Karst Plain Project and Black Abyss Productions. I'm your host and producer of all things ecology at WFSU, Rob Diaz de Villegas.